Hello and welcome. Enrichment today. 5-star definite integral. Integral from 0 to pi log of sine x dx is equal to minus pi log 2. It does not require further maths, so that's good. So just not basic, obviously it's enrichment, just knowledge from straight maths will actually do for this particular integral. This is how it's done. We're going to call I our required integral. So that's basically the value of what we're trying to find. The first step is actually the crucial step for this particular integral, and perhaps you need to have seen a lot of these special integrals as part of your regular training to be aware why you're doing it. So first of all is to notice that the sine of x is even about pi over 2. So what this means, basically, if you think about the graph of sine of x, something like that, is symmetrical about pi over 2, same area basically. But in our case, we're not looking at the area under the graph of sine of x, we're looking at the values that we generate basically, these heights, when we're putting different values for the sine of x, and then obviously we'll be logging the values. Whatever we're getting from 0 to pi over 2, we should be getting from pi over 2 to pi. And therefore, this means we can actually write this particular integral as two lots. The integral from 0 to pi over 2 log of sine x dx. And the reason we've done that is to facilitate a very special substitution. And the substitution that we want to do is to actually swap the limits and change the sines into causes. I think it's, I don't know if they're called the complementary or supplementary. It's complementary identities for sine and cos. We want to facilitate those. So the way we do that, we're going to use a substitution. Little x, which we have in our integral, is equal to pi over 2 minus big X, or if you want, you can actually swap it asymmetrical minus x. Differentiating the first line, my dx in lowercase is minus my dx in uppercase, and the limits will swap. So the limit of 0, when we're putting little x is equal to 0, it will map to pi over 2. And when we're putting pi over 2 for our little x there, it will go to 0. So we're ready now to move this particular integral into the big X variable. The limits swapped. The log of the sine of pi over 2 minus big X, close argument, and my d little x is minus d capital X. Okay, now what happens in there? First of all, I'm going to write again on the next line, it's probably better. I is equal to two lots. I'm going to use the minus from the dx to swap the limits back to where they were. 0 to pi over 2. And of course, this is what I mean about this complementary, or maybe they're called supplementary, I'm not quite sure about what they're called. The sine of pi over 2 minus x, actually let's write it in uppercase, it doesn't really matter. It's in fact the same as the cos of x, and symmetrically, although we don't actually have it in there now, the cos of pi over 2 minus big X will be equal to the sine of x. These are symmetrical identities and very, very useful. Okay, so now this thing here is quite clearly the cos of x. So we have got now the log of the cos of big X dx. So now, pardon me, comes the next step. I is of course this quantity here, and I is also this quantity here, and of course all of these are equivalent, so I can actually say the following: I plus I is equal to, well, For the first I there, I can use this quantity here. So I can actually say that's 2 lots of 0 to pi over 2, the log of the cos of, actually, this will be capital there, beg your pardon, dx, plus, I can use for the second I, that, but I prefer, because of course I want the same limits, to actually say it's the same as that, which of course it is. 0 to pi over 2, the log of the sine of x dx in lowercase. Does lower or upper matter in this particular case? Well, the answer is not really. So at this stage, I'm going to be a bit sloppy. It hardly matters the integral, whether we write everything in little x, in y's, in t's, in thetas, or whatever you want, it's exactly the same. So just to make it easier, I'm going to put the dx back into lowercase. Or I could have done it the other way around and leave big x's in there. It doesn't really matter. Okay, so this allows me on the next line to put the two integrals together because they have the same limits. There's also a shared 2 at the front, a multiplicative 2. So pi over 2, and we got the log of the cos of x plus the log of the sine of x dx. And now on the next line, using the rules of logs, 2i is going to be, of course, 2 lots integral 0 to pi over 2, and we've got the log of addition of logs, multiplication of the arguments, and therefore we're going to have the cos of x times the sine of x. And obvious manipulation at this particular stage, of course, it should be that we can get rid of the 2's from the front of the integral and write the 2 trig bits as a single trig function. So let's do that. So our I is going to be equal to 0 to pi over 2. The log cos x sine x, we can write it as a half sine of 2x dx. Okay, so what next? That is the question. Again, we continue with the rules of logs because again we have a multiplication, half times the sine of 2x, so that's of course 0 to pi over 2, the log of a half plus the log of the sine of 2x dx. Okay, what happens next? I again, that's this I there, is equal to, this is just a constant, so I can split the integral now into 2 bits. So I can actually say, well, this is the same as 0 to pi over 2, log of a half, which of course is a constant, dx, plus the integral from 0 to pi over 2, the log of the sine of 2x dx. And it looks like I'm chasing my tail, so I'm not going anywhere. But this particular integral is actually, it reminds me of this particular one, if only that 2 wasn't there. So I'm going to use another substitution just for the second integral. Or perhaps what I should do is maybe evaluate that and say the following. So that is integrating that between 0 and pi over 2, you can just check that very quickly, is pi over 2 times the log of a half plus, now I'm going to use a substitution for this particular integral. Of course, the substitution I want to use is something that will take me into a single variable argument, like a theta or something like that. So I'm going to use a theta or something. So I'm going to say let, in this particular case, let theta is equal to 2x. So what happens now? Well, my d theta first of all, or actually let's write it again as a half theta is equal to x, and my dx is of course a half d theta. What happens to the limits now? The limits will change. Is that unfortunate, or is it, will it work all right for us? Okay, let's check what happens. When we're putting x is equal to pi over 2, so the pi over 2 that we have in there will map now into pi, and the 0, whether we double it or not, is still into 0. So this integral now will become plus 0 to pi, the limits have now changed, and what do we have? We have the log of the sine of theta, the 2x is of course theta, and the dx is of course a half d theta. Okay, couple of things to do. And that's probably the last line I could just about fit in there. The log of a half is of course minus log 2, so that's going to be minus pi over 2 log 2. Interesting to see we're getting something which resembles our answer, but for a factor of 2 or a half if you see it the other way around. And what there is this now? Plus, this is a constant, we can write it on the outside, a half integral 0 to pi, the log of sine theta d theta. But if we go and look back at our original definition and look at this particular line, I is the integral from 0 to pi log of sine x dx. Here we have log of sine theta d theta. It hardly matters whether you want to call it theta, as I said before, it's the same value. So I'm going to squeeze it up here, the very last few lines for this particular integration. I don't want to be wrapping all of this off. So what we get is I there is equal to minus pi over 2 log 2 plus a half. That's the half that we have in front of this integral. And of course, this integral is just I. We can double both sides of this equation, so we can actually say 2 lots of I is equal to minus pi log 2 plus I, and all we need to do is to subtract this side to the left. So our integral is in fact minus pi log 2 as required. I hope you found this interesting, this particular technique. I'll try to do a few videos that are very similar in their manipulation, just give you more working practice. I think the old AEA step papers, they used to kind of like have questions which were based on this technique. I don't know if they still do. I haven't really looked at these papers for a number of years now, but this is where I first came across this kind of thing when I was looking at this very special papers. Okay, I hope you enjoyed it. I hope you found it useful, and I'll be back with you real soon. Bye for now.